From almost anywhere on Earth, the sun seems impossible to miss. It fills the day with light, warms the ground beneath us, and hangs in the sky as the most obvious destination beyond our world. Pluto is nothing like that. It is so distant and faint that even under a perfectly dark sky, no human eye could find it without help. If we placed both destinations on a simple map, the choice would appear absurdly easy. The Sun is our nearest star. Pluto waits near the outer reaches of the solar system. Surely the shorter journey should be the simpler one. Imagine a spacecraft floating just above Earth. Ahead of it is the Sun, enormous and bright. Far behind that brilliance, separated by billions of kilometers, lies Pluto. If the spacecraft needed to reach the Sun, we might expect the solution to be simple. Point it toward the light, fire the engines, and let the Sun's gravity finish the journey. Even switching the engines off may seem sufficient. The Sun holds the planets in their paths. Why would it not pull an unpowered spacecraft straight down? Yet that is not what happens. A spacecraft released from Earth does not simply drop toward the Sun. It continues moving around it. The engines may be silent, but the spacecraft is not still. It carries something away from Earth that cannot be seen in a photograph of the launch and cannot be measured by looking only at the distance to its destination. That hidden inheritance keeps turning an apparently direct fall into a journey that misses the Sun again and again. The history of exploration makes the contradiction even sharper. New horizons left Earth and crossed the enormous darkness between the inner solar system and Pluto. After nearly a decade of travel, it passed the distant world and returned close views of a place that had once been little more than a blurred point. Humanity had reached Pluto with a small robotic spacecraft. But reaching close to the Sun required a very different kind of journey. Parker's solar probe needed an exceptionally powerful launch, followed by repeated encounters with another planet that gradually changed its path. The target was visible from Earth every clear day. Still, the spacecraft could not take the route that common sense seemed to offer. This does not mean Pluto is easy, or that the Sun is impossible to approach. Both missions demanded extraordinary precision. The comparison reveals something more useful. Distance alone does not decide how difficult a journey through the solar system will be. A destination can be nearby and still require a greater change in motion. Another can be unimaginably remote, yet lie along a path that a spacecraft can follow. That difference changes the question completely. We are no longer asking which object is closer on a chart. We are asking what a spacecraft must do to the motion it already has, what kind of encounter counts as arrival, and what price its engines must pay for changing course. The answer will emerge from two journeys moving through the same solar system under identical laws, yet demanding opposite strategies. One traveled outward toward darkness. The other had to find a way inward toward light. Before those paths can be compared honestly, however, we must decide what reaching either destination actually means. Flying past a world is not the same as stopping beside it, and passing close to the Sun is not the same as landing on its surface. Only then can we identify the invisible motion that turns the closest target into the deeper challenge. The word reaching sounds simple until a spacecraft arrives. On Earth, reaching a place usually means stopping there. A traveler reaches a city by entering it, slowing down, and remaining for a while. Space missions do not always work that way. A spacecraft can cross the region around another world, collect its observations in a few hours, and continue into the darkness without ever becoming a permanent companion of its target. That still counts as reaching the destination, but it is not the same achievement as entering orbit or landing. New Horizons reached Pluto in this limited but important sense. It flew through the Pluto system, passed close enough to study the dwarf planet and its moons, and then continued outward. It did not carry the fuel and equipment needed to cancel its arrival speed and settle into orbit. It did not attempt to land. Its mission was designed around a single fast encounter, so its journey can only be judged fairly as a flyby. Parker's solar probe also requires careful language. It does not travel to the sun and stop beside it. It cannot hover above the sun like an aircraft above a landscape. And it cannot land on a solid solar surface because no such surface exists. Parker follows a stretched orbit around the sun. During each circuit, it sweeps inward, reaches its closest point, and then moves outward again. That closest point is called perihelion. When we speak of flying over the sun in this investigation, we mean achieving a very low perihelion, comparable to Parker's close passes. The comparison is therefore not between landing on Pluto and landing on the Sun. It is not between building permanent stations at either destination. It is between sending a small robotic spacecraft past Pluto and sending another small robotic spacecraft through the region close to the Sun while it remains in solar orbit. These missions are not identical, but their goals are defined clearly enough to expose the unusual difference in the journeys required from Earth. The word easier also needs a boundary. A mission can be difficult in several ways. It can demand an unusually powerful launch. It can require years of travel. Its spacecraft may need to survive intense heat, deep cold, harmful radiation, weak sunlight, or long communication delays. It may carry little scientific equipment because most of its mass must be devoted to propulsion or protection. It may have only one chance to collect its most important observations. All of those problems matter, and they will later prevent us from calling either mission easy in an absolute sense. For the central comparison, however, easier refers mainly to the change in motion needed to place a useful spacecraft on the required path. This includes the burden placed on the launch vehicle, the spacecraft's propulsion system, and any planetary encounters used to reshape the trajectory. Travel time and environmental survival remain important, but they answer different questions. Engineers often describe part of this motion problem with delta V. The name means change in velocity. It is not simply the speed shown on a spacecraft's imaginary speedometer. It represents how much the spacecraft must change its motion through thrust. A burn may increase speed, reduce it, or turn the velocity in another direction. Each change consumes part of the mission's limited propulsion capability. Launch trajectories are also described with a quantity called C3, or characteristic energy. In plain terms, C3 expresses how much excess energy a spacecraft has as it escapes Earth's immediate gravitational control. It is based on the square of the spacecraft's excess speed. A larger C3 usually demands more from the launch vehicle and leaves less capacity for payload, although the complete mission still depends on direction, timing, and later encounters. Speed, delta V, and C3 are related, but they are not interchangeable. A spacecraft may be moving extremely fast because gravity has accelerated it, even though its engines did not provide that entire speed. It may perform a small burn that creates a large change in its later path. A launch can have a high C3 without that number describing every velocity change during the whole mission. Treating these values as different names for one measurement would create a false comparison. The reference point matters as well. A speed measured relative to Earth may differ from the same spacecraft's speed relative to the Sun. Near Pluto, Engineers may care about its motion relative to Pluto itself. None of these figures is automatically wrong. They answer different questions. Problems begin only when a speed from one reference frame is placed beside a number from another, as if both describe the same motion. This distinction protects the investigation from a mistake. If a Pluto orbiter were compared with a probe passing near the Sun, the result would reflect different goals rather than different routes. If a solar impact were compared with a Pluto flyby, the word reaching would hide a mismatch. A comparison must hold mission types steady enough for the physics to become visible. It need not make the spacecraft identical, but it must ensure that the conclusion does not depend on changing what success means within the argument. With these boundaries in place, the title becomes a testable claim rather than a dramatic slogan. We will compare an achievable Pluto flyby with an achievable closed solar pass, focusing first on trajectory, energy, and propulsion. We will then return to the other kinds of difficulty that each environment creates. This will preserve the surprising truth, without pretending that every possible journey to Pluto is easier than every possible journey toward the Sun. The rules of the comparison are now clear, but the reason for its strange result remains hidden. Both spacecraft begin from the same planet, and neither begins its journey from rest. Before we can understand why one path carries a probe outward, while the other demands repeated effort to move inward, we must examine the motion that Earth gives to everything launched from its surface. Every journey begins before the engines ignite. A rocket may appear motionless on its launch pad, held upright against the sky, but stillness depends on where the observer is standing. To someone beside the pad, the vehicle is at rest. Seen from farther away, it is already taking part in several motions at once. Earth is turning beneath it. Earth is also traveling around the Sun. The entire launch site, the rocket, its fuel, its instruments, and every person watching are being carried through space together. Earth's rotation gives a rocket some motion around the planet, which is one reason launch sites and launch directions matter. But the larger motion for this investigation is Earth's journey around the Sun. Our planet completes that journey once each year, covering an orbit so large that its everyday speed is difficult to imagine. Earth moves around the Sun at a mean speed of about 29.78 kilometers every second. That is nearly 30 kilometers per second, or roughly 67,000 miles per hour. The word mean matters because Earth's orbit is not a perfect circle. Its speed changes slightly during the year. Yet the rounded figure is accurate enough to reveal the scale of the problem. In a single second, Earth travels farther along its orbit than many people travel to work. In the time required to read a short sentence, the planet has moved hundreds of kilometers through space, carrying everything on its surface with it. We do not feel this motion because we share it. The atmosphere, oceans, buildings, and our bodies move with Earth. There is no sudden wind produced by Earth's orbit because the surrounding atmosphere is traveling too. The situation is similar inside a smoothly moving vehicle. Passengers can speak, walk, or place an object on a table without constantly accounting for the vehicle's speed. Their smaller motions happen inside a larger motion they all share. A spacecraft begins in the same condition. Before launch, it is already moving around the Sun with Earth. Rising away from the ground does not erase that motion. Even after the spacecraft escapes Earth's immediate gravitational control, it still carries the heliocentric movement it inherited from its home planet. Its engines can change that motion, and gravity can reshape it, but neither the launch tower nor the edge of Earth's atmosphere provides a reset button that makes its solar speed disappear. This is why direction matters as much as the number itself. Earth's motion around the Sun is mainly sideways relative to the line joining Earth and the Sun. Engineers call this direction tangential because it runs along Earth's orbital path rather than directly inward or outward. A spacecraft leaving Earth therefore starts with a powerful sideways motion around the Sun, even if its nose appears to point toward a completely different destination. That inherited velocity can help or hinder a mission depending on how the required path differs from Earth's path. A spacecraft does not pay merely for the distance ahead. It must change the velocity it already possesses into the velocity its new route requires. The difference includes direction as well as speed. Two vehicles moving at the same numerical speed can have very different velocities if they are moving in different directions. To describe these motions clearly, we need to keep our reference points separate. Imagine watching a spacecraft depart while standing on Earth. From that viewpoint, its Earth relative speed measures how quickly it is moving away from our planet. This is the kind of figure commonly quoted when a launch is described as exceptionally fast. It tells us something important about the power of the departure, but it does not describe the spacecraft's complete motion around the Sun. Now imagine observing the same spacecraft from a position fixed relative to the Sun. Earth itself is racing across this wider view, and the spacecraft's departure is added to or subtracted from the motion it inherited. Its heliocentric speed may therefore differ greatly from the Earth relative figure. The exact result depends on the direction of launch and the path selected by mission planners. A third speed becomes important near the destination. As a spacecraft passes Pluto, for example, engineers may describe how fast it moves relative to Pluto. Pluto is not stationary either. It travels along its own path around the Sun. The encounter speed measures the difference between the motions of the spacecraft and Pluto at the moment they meet. That number is not automatically the spacecraft's speed relative to Earth or the Sun. One spacecraft can therefore have several correct speeds at the same moment. An observer traveling with Earth, an observer fixed relative to the Sun, and an observer moving with the target would each measure something different. This is not a disagreement about reality. It is a consequence of asking how quickly one moving object changes position compared with another moving object. The distinction protects us from misleading comparisons. New Horizons could leave Earth at one quoted speed, travel around the Sun at another, and pass Pluto at a third. Selecting whichever number sounds most dramatic would tell us little about the actual burden placed on its rocket. The same warning applies to Parker Solar Probe, whose speed near the Sun becomes enormous, even though the central challenge is how it changes the solar orbit it inherited from Earth. A thought experiment makes the point clearer. Suppose two probes leave Earth with equal Earth relative speed, but one departs in the direction Earth is traveling while the other departs against it. An observer on Earth may describe similar departures. From the Sun's viewpoint, however, the first probe adds its launch motion to Earth's motion, while the second subtracts from it. Their paths can separate, even though their launch speeds sound alike. The solar system does not respond to the number printed in a headline. It responds to the velocity of each probe, its speed, its direction, and the moving frame from which it began. The hidden starting condition is now visible. Every interplanetary spacecraft launched from our world begins on a platform already sweeping around the Sun at nearly 30 kilometers per second. That motion is not a minor detail added after distance is measured. It determines the shape of every possible route leaving Earth. Yet one question remains. The Sun's gravity is always pulling inward. If a spacecraft is already under that pull, why does its sideways motion prevent a direct fall? To answer that, we must see an orbit not as a place where gravity has stopped working, but as a fall that never reaches the ground. Gravity never stops pulling Earth toward the Sun. The same is true for a spacecraft that has escaped Earth's immediate control. Yet neither object travels straight into the star. The reason is not that gravity becomes weak or switches off. The reason is that inward fall happens at the same time as powerful sideways motion. While gravity bends the path toward the Sun, the object keeps moving across the direction in which it is falling. A familiar thought experiment helps make this visible. Imagine standing on a mountain so high that the curve of Earth can be seen below. Drop a stone, and it falls almost straight down. Throw another stone horizontally, and it travels some distance before reaching the ground. Throw it faster, and the surface curves away beneath it while it falls. At a sufficient sideways speed, the stone continues falling, but the curved ground falls away at the same rate. The stone keeps missing Earth. It has entered orbit. This picture is useful, but it has limits. A real mountain cannot rise beyond the atmosphere, and air resistance would slow the stone. In space, there is no solid track supporting the orbiting object. Solar system trajectories also involve planets that are moving while their gravity alters a spacecraft's path. The analogy should therefore illustrate one idea only. An orbit is not an escape from gravity. It is a continuing fall, combined with enough sideways motion to keep missing the central body. Earth does this around the Sun. Every moment, solar gravity turns Earth's velocity slightly inward. If the Sun suddenly vanished, Earth would no longer curve around an empty point. It would continue in the direction it was moving at that instant. The Sun's gravity continuously bends that otherwise straighter motion into an orbit. A spacecraft leaving Earth inherits a similar starting direction, so solar gravity begins shaping its path from a state already close to Earth's orbit. This shows why the phrase "falling toward the Sun" can be misleading. Every planet is falling toward the Sun, but each also carries enough sideways motion to remain in orbit. A spacecraft does not begin outside this system and enter it from a standstill. It begins as part of the moving arrangement. Its task is not to activate gravity, which is already acting, but to alter the balance between inward pull and sideways travel until the orbit reaches the required depth. Pointing the spacecraft toward the Sun does not remove this sideways velocity. A spacecraft can turn its nose without immediately changing the direction in which its entire mass is moving. Only thrust or another external force can produce that change. If its engines stop after the turn, the vehicle continues along its existing path while facing somewhere else. Orientation and velocity are not the same thing. The strength of an object's rotational motion around the Sun can be described through angular momentum. In this setting, angular momentum depends on the object's motion across the sunward direction and on its distance from the Sun. The exact mathematics is not needed to understand the consequence. An object carrying substantial sideways motion cannot reach a very small solar distance unless that angular momentum is reduced or redistributed. This is why a close solar journey begins with a surprising action. Instead of simply accelerating toward the Sun, the spacecraft must oppose some of the motion it already has around the Sun. A thrust made against the direction of travel is called a retrograde burn. It reduces the spacecraft's tangential speed and lowers its angular momentum. Solar gravity can then pull the vehicle into a path that passes closer to the star. The new path is normally not a straight line. It is another orbit, but a more stretched one. The burn changes one part of the orbit, causing the opposite side to move inward. The closest point, the perihelion, becomes lower. Unless still more motion is removed, the spacecraft sweeps rapidly through that low point and travels outward again. Reaching close to the Sun, therefore, means carefully shaping an orbit, not driving along a direct road. Burning in the opposite direction produces a different result. A prograde burn adds speed in the direction the spacecraft is already traveling. This generally adds energy to its heliocentric orbit. If the burn is performed near Earth's distance from the Sun, the far side of the new orbit can rise outward. With enough added energy, the route can reach the regions of the outer planets or even become an escape path from the solar system. The contrast reveals why the same starting motion can be useful for one destination and troublesome for another. An outward mission can add to Earth's inherited motion in a carefully selected direction. A close solar mission must take away a large part of the motion that keeps Earth safely circling the Sun. One mission works with the moving platform. The other must first undo much of what that platform provides. Engineers often describe an orbit using specific orbital energy. The word specific means the quantity is measured for each unit of mass, allowing different spacecraft to be compared without simply favoring the heavier one. This orbital energy combines two conditions: how fast the spacecraft is moving and where it is inside the Sun's gravitational field. Changing either condition changes the shape of the possible orbit. An object close to the Sun can move faster than an object farther away, even if no engine is firing. As it falls inward, gravitational potential is converted into motion. The spacecraft accelerates because of the Sun's gravity. Later, as it climbs outward, it slows again. This creates an important distinction. The highest speed reached during a mission does not reveal how much work the spacecraft's engines performed. A probe may become extraordinarily fast near perihelion precisely because it previously lost enough orbital energy to fall deeply into the Sun's gravitational field. The engines did not directly supply all of that final speed. Gravity produced much of it during the inward fall. Judging mission difficulty by peak speed would therefore hide the harder earlier task of lowering the orbit. The same logic explains why reducing speed at one point can lead to greater speed later. A retrograde burn near Earth's orbit slows the spacecraft at that location, allowing it to fall closer to the Sun. During the fall, gravity accelerates it. By the time it reaches perihelion, it may be moving much faster than before the original slowing maneuver. There is no contradiction, because the speeds are measured at different places within the gravitational field. Direction remains central throughout the process. A burn that changes only the orientation of velocity can reshape an orbit even when the change in numerical speed is modest. A burn in the wrong direction can raise perihelion instead of lowering it. Mission planners must therefore choose the moment, direction, and size of each change so that the resulting path intersects the intended region at the intended time. The provisional answer is now clear. A spacecraft does not fall directly into the Sun because it begins with strong tangential motion inherited from Earth. Solar gravity bends that motion into an orbit, producing a fall that keeps missing the star. To pass much closer to the Sun, the spacecraft must reduce its sideways velocity, angular momentum, and orbital energy. The problem is not discovering which way the Sun lies. It is changing a motion that already carries the spacecraft safely around it. That answer creates a more practical question. If lowering perihelion requires canceling so much inherited motion, why not build a rocket powerful enough to perform the entire change directly? The obstacle appears as soon as the required change is translated from orbital geometry into fuel, mass, and the limits of chemical propulsion. Once the route is understood, the problem moves from geometry to machinery. A close solar pass requires a spacecraft to remove a large share of the sideways motion it carries from Earth. Engineers express the size of that required change as delta V. The question is no longer whether an inward path exists. Physics allows such a path. The question is whether a rocket can place a useful spacecraft on it while carrying enough structure, protection, communications equipment, and scientific instruments to complete the mission. For a direct solar trajectory from near Earth, estimates of the required change commonly fall into a range of roughly 24 to 30 kilometers per second. This should not be treated as one exact universal price. The answer changes with the spacecraft's starting orbit, the launch vehicle, the direction and timing of departure, the desired solar distance, and whether another planet is allowed to help reshape the route. A trajectory aimed at direct impact is also different from one designed for repeated close passes. Even with those qualifications, the scale is severe. The required change is not a modest correction added after an ordinary launch. It is comparable to removing most of the heliocentric motion inherited from Earth while also dealing with the effort needed to escape Earth's immediate gravitational hold. A vehicle that attempted to perform the whole task through direct chemical propulsion would face a mass problem that grows much faster than intuition suggests. A chemical rocket changes motion by throwing mass in the opposite direction. Hot gas rushes from the engine, and the rocket gains velocity in response. To continue accelerating, the vehicle must carry more propellant. That sounds simple enough. If one quantity of fuel provides one useful change, perhaps several times as much fuel should provide several times the result. But a rocket must accelerate its fuel along with everything else. Propellant reserved for a later burn has mass during every earlier burn. Tanks have mass. Engines have mass. The structure holding them together has mass. If more propellant is added, the rocket must now accelerate that extra propellant and the larger equipment required to contain and use it. Carrying the solution makes the original problem heavier. This creates the relationship described by the rocket equation. The important point is not the formula itself, but the way the requirement grows. Delta V does not increase in a simple straight line with the amount of propellant. Each additional step demands a larger ratio between the vehicle's initial mass and the mass left after the propellant is expelled. As the target delta V rises, the required starting mass grows rapidly, while the useful final mass becomes a smaller fraction of the whole. Imagine packing supplies for a journey in which every extra kilogram of food requires additional food to carry it. The comparison is imperfect because rockets do not consume propellant as food, but it captures the compounding burden. The vehicle must spend part of its propellant accelerating propellant that will only be used later. At extreme requirements, most of the starting mass exists merely to move and contain the material that will soon be thrown away. Staging makes rockets far more capable. When a stage has emptied its tanks, the vehicle discards the tanks, engines, and supporting structure that are no longer useful. Later stages do not have to keep accelerating all that dead mass. This is why launch vehicles are built in sections rather than as one enormous tank connected to one engine. But staging does not repeal the rocket equation. Every stage still needs structure, engines, guidance, and margins for safe operation. Upper stages must be lifted by the stages beneath them. Adding stages can improve the practical result, but complexity and mass grow with them. Eventually, attempts to purchase ever more delta V leave too little capacity for the spacecraft that the mission was meant to send. That remaining spacecraft must be more than an empty shell. Near the sun, it needs protection, power, guidance, communication, and instruments. Removing those systems to reduce mass could make the launch easier while making the mission pointless. Engineering success is not achieved when a final fragment follows the correct mathematical path. A useful payload must survive the launch, navigate the trajectory, operate at the destination, gather evidence, and return information to Earth. The payload fraction is what turns the calculation into a mission decision. A launch vehicle may begin with an enormous total mass, yet only a small part of that mass reaches the final trajectory. If the required delta V rises, mission designers cannot simply preserve every instrument and enlarge the fuel tanks without limit. Something must give. The payload may shrink, the target path may be relaxed, the spacecraft may accept a longer journey, or the design may seek help from gravity. In this way, the rocket equation shapes not only the vehicle, but the science itself. It decides how many instruments can fly, how much protection they receive, and how much fuel remains for corrections after launch. The direct approach also concentrates risk into one demanding departure. A workable mission needs more than a theoretical velocity change. It needs navigation margins, correction capability, reliable systems, and enough operating life to handle unexpected conditions throughout the journey without exhausting options after launch. This distinction separates theoretical possibility from practical capability. Nothing in orbital mechanics forbids a direct burn that removes enough sideways motion. If an ideal vehicle possessed unlimited propellant or a propulsion system with extraordinary performance, it could produce the change. Real chemical rockets operate with limited exhaust velocity, finite structural strength, and payloads that must remain large enough to do meaningful work. Under those conditions, the direct approach becomes an extremely poor bargain. NASA has expressed the difficulty with a striking comparison made in the context of Parker's solar probe. Reaching the Sun takes about 55 times more energy than reaching Mars. The statement captures how misleading distance can be. Mars is farther from Earth than the Sun appears to be, yet traveling toward the Sun requires shedding the sideways motion shared with Earth. The number must be used carefully. It is an official mission explanation, not a universal conversion rule for every spacecraft and every endpoint. Energy can be defined in different ways across mission discussions. Payload, launch conditions, assists, and arrival goals matter. Most importantly, the figure compares the Sun with Mars in Parker's explanatory context. It does not prove that the Sun is exactly 55 times harder to reach than Pluto, and it should never be repeated as though it does. The value of the comparison is not a dramatic multiplier. It is the physical lesson behind it. A destination's distance on a map does not reveal how far a spacecraft's velocity must move from its starting state. Mars requires a change from Earth's orbit, but a deep solar approach requires a much greater loss of heliocentric energy and angular momentum. The nearby target can therefore demand the larger propulsion change. At this point, a larger rocket may still seem like the answer. More powerful launch vehicles can send smaller payloads onto more demanding trajectories. They can provide high departure energy and reduce the work left for the spacecraft. Yet even the strongest practical chemical launch system cannot deliver a substantial scientific probe through a single clean maneuver that cancels nearly all of Earth's solar motion. The mass sacrifice to propellant and stages overwhelms the useful mission. The rocket equation therefore acts like a wall, but not an absolute wall in nature. It is a wall for a particular method, carrying chemical propellant and using it to purchase the entire velocity change directly. The orbit still exists, and the Sun continues to pull inward. What fails is the straightforward plan of doing all the braking with fuel brought from Earth. Parker Solar Probe's success shows that engineers found another route through the problem. The mission reached closer to the Sun than any earlier spacecraft, without carrying enough propellant to cancel Earth's motion in one vast burn. It divided the required change across time and used an external moving body to alter the orbit. That turns the limitation into a new question. If the spacecraft could not carry the full braking power with it, where could that lost orbital energy go? The answer waited on a nearby world whose gravity could perform the repeated work that chemical propulsion could not. The nearby world that made Parker Solar Probe's journey possible was Venus. It did not provide fuel, a landing place, or a mechanical push. Its contribution came from motion and gravity. By passing Venus along carefully chosen paths, Parker could transfer part of its unwanted heliocentric orbital energy to the planet. Each encounter changed the spacecraft's solar orbit without requiring Parker to carry the propellant that an equivalent direct braking maneuver would have demanded. Parker still needed an exceptionally powerful launch. Leaving Earth and entering the correct first solar orbit required a launch vehicle capable of delivering a small but heavily protected probe onto a demanding trajectory. Yet even that launch was only the opening move. It did not place Parker immediately into its deepest orbit, and it did not cancel the full sideways motion inherited from Earth. Instead, the mission was designed as a long sequence. Parker traveled inward, past the Sun, moved outward again, and returned toward the orbit of Venus. At selected encounters, the spacecraft approached Venus with the timing and direction needed to alter its heliocentric path. After each successful pass, its next solar orbit reached closer to the Sun. The descent was measured not as one continuous plunge, but as a series of increasingly deep arcs. Parker completed 7 gravity assists at Venus. These encounters unfolded across roughly 6 years, ending with the 7th Venus flyby in November 2024. That final encounter moved the spacecraft into the orbital pattern required for its closest solar passes. What a chemical rocket could not economically accomplish in one direct burn was achieved gradually through repeated contact with the gravitational influence of a moving planet. The phrase gravity assist can sound as though Venus supplied something without paying for it. That is not what happened. The spacecraft entered the region around Venus, curved through the planet's gravity, and departed along a different direction. From a viewpoint moving with Venus, the spacecraft's path was bent. Its incoming and outgoing speeds, relative to the planet, remained closely related, apart from small-powered corrections and real-world complications. The important change becomes visible from the Sun's viewpoint. Venus itself moves rapidly around the Sun. Parker approached and departed this moving gravitational field in geometry chosen so that its heliocentric motion was reduced. The spacecraft left the encounter with a different direction and less orbital energy around the Sun than it carried before the pass. Its next perihelion could therefore lie deeper inside the solar system. That energy did not disappear. Momentum and energy were exchanged with Venus's orbital motion. The planet received the matching opposite change, but Venus is so much more massive than Parker that the effect on its orbit was unimaginably small. The spacecraft's path changed dramatically, while the planet continued along an orbit that was, for every practical purpose, unchanged. Conservation laws remained intact. Calling Venus a break is therefore useful if the comparison is kept under control. No surface rubbed against the spacecraft, and no braking force acted continuously. Venus served as a moving gravitational partner. During a brief encounter, its gravity redirected Parker's motion in a way that reduced the probe's energy relative to the Sun. The result resembled braking in the wider heliocentric frame, even though the local encounter was a smooth gravitational turn. one pass was not enough. The first assist lowered Parker's orbit, but the spacecraft still retained too much angular momentum to reach its final perihelion. The revised orbit brought it back into position for later encounters. Mission planners used each return as another opportunity to remove a portion of orbital energy. Small reductions accumulated across years until the orbit became far more stretched than the path established at launch. This stepwise design offered more than a substitute for fuel. It made the extreme trajectory controllable. Each solar orbit and planetary encounter could be tracked. Corrections could preserve the next meeting with Venus. The mission unfolded through a chain in which every successful pass prepared the geometry required for the one that followed. A failure to arrive at the right place and time could have broken that chain. Repeated assists changed the meaning of precision. Venus and Parker were never waiting at fixed points for the next meeting. Both continued orbiting the Sun, so every encounter depended on the earlier one delivering the spacecraft into the correct path. The target was not the planet's position, but the place Venus would occupy when Parker returned. Timing errors could become position errors, and position errors could change the gravitational turn. The mission therefore relied on predictions, tracking, and measured corrections across a moving system rather than on one aimed launch. The sequence protected the scientific payload from the direct burn mass problem. Parker could devote mass to its heat shield, instruments, communication systems, and guidance instead of carrying the enormous propellant supply demanded by complete chemical braking. Venus did not make those systems weightless, and the powerful launch remained necessary. It changed which burden the mission had to carry. Fuel mass was replaced by careful geometry, repeated opportunities, and time. This trade did not make the journey simple, but it converted a nearly unusable direct design into a mission that could carry functioning instruments close enough to examine the solar environment. The patience demanded by the sequence is part of the engineering. A direct route is often imagined as the bold option because it appears fast and simple. Parker's actual path was more subtle. The spacecraft repeatedly moved away from the Sun after approaching it. Those outward sweeps were not failures or retreats. They were necessary parts of an orbit that returned Parker to Venus and allowed the next reduction in energy. After the final Venus encounter, Parker entered its deepest operational orbit. In December 2024, it passed about 3.8 million miles above the Sun's visible surface, closer than any previous spacecraft. The distance must be described from the surface, rather than confused with distance from the Sun's center. Even at millions of miles, Parker was traveling through the Sun's outer atmosphere and operating in conditions no earlier mission had sampled so directly. Near that closest approach, Parker moved at roughly 430,000 miles per hour relative to the Sun. This made it the fastest human-made object. Yet the record does not mean its engines directly accelerated it to that speed. The earlier Venus encounters had removed orbital energy and allowed the spacecraft to fall much deeper into the Sun's gravitational field. During that inward fall, solar gravity converted position into speed. The apparent contradiction is central to Parker's journey. Venus slowed the spacecraft's motion around the Sun in the way needed to lower its orbit. The lower orbit then carried Parker into a region where the Sun's gravity accelerated it to an extraordinary perihelion speed. Parker became faster near the Sun because it had first been placed on a path with less heliocentric orbital energy than the one it inherited from Earth. This is why peak speed cannot measure the launch burden by itself. A viewer comparing only final velocities might assume Parker's rocket supplied every mile per hour recorded near perihelion. In reality, the mission architecture separated the problem into stages, launch onto the first useful orbit, repeated gravitational reductions through Venus, and acceleration during the final solar fall. The record speed was the result of the entire path. Venus, therefore, solved the practical problem left by the rocket equation. Parker did not need to store enough chemical propellant to perform one immense retrograde maneuver. It exchanged energy with a planet, returned, and repeated the process 7 times. The cost moved from an impossible mass of fuel toward years of precise navigation, carefully aligned encounters, and a spacecraft capable of surviving every passage. The local answer is complete. Parker reached the Sun's outer atmosphere because Venus gradually reduced the sideways motion and orbital energy that kept the probe farther away. The closest target became reachable only after the mission stopped treating the journey as a direct line and began using the motion of another world. But this creates an apparent conflict. Gravity assists are often described as slingshots that make spacecraft faster. Parker used Venus to slow down, while another probe used Jupiter to shorten its journey into the outer solar system. To understand how the same basic process can produce opposite results, we must first follow the spacecraft that took the fast road toward Pluto. New Horizons began its journey in January 2006 with a mission built around speed. Pluto was more than 3 billion miles away along the route ahead, and the spacecraft had to arrive while its instruments, power source, communication system, and operations team could still complete a useful encounter. A slow transfer might reduce some launch demands, but it would extend the mission across a much longer part of a human career. The chosen architecture accepted a difficult departure in exchange for a journey measured in less than a decade. The spacecraft was small compared with the launch system beneath it. An Atlas V 551 carried New Horizons away from the ground, while a Star 48B upper stage supplied the final push needed for its rapid Earth departure. The combination sent the probe away from Earth at approximately 16.2 kilometers per second relative to our planet. At the time, this was the fastest departure from Earth achieved by a spacecraft. That distinction needs the same care applied to Parker's record. New Horizons did not remain the fastest human-made object under every possible measurement. Its 16.2 km per second figure describes departure relative to Earth. Its motion around the Sun was different, and its speed relative to Pluto at encounter was different again. Parker later reached a far higher heliocentric speed while falling near the Sun. The records describe different moments and reference points. Mission planners also described the departure through a C3 of about 158 square kilometers per square second. C3 represents the square of the excess speed a spacecraft retains after escaping Earth's immediate gravitational influence. A high value signals a demanding launch and a trajectory carrying substantial energy away from Earth. It does not equal the spacecraft's speed throughout the mission, nor does it include every later change produced by planetary gravity. The launch direction mattered as much as the launch power. New Horizons departed along a path that used Earth's existing heliocentric motion and added the change needed to raise the spacecraft's route toward the outer solar system. It did not need to erase nearly all the sideways speed inherited from Earth. The spacecraft left on an outward, high-energy solar path that could cross the region of the giant planets. Even that powerful start was not the complete route to Pluto. The spacecraft first traveled toward Jupiter, reaching the giant planet in February 2007. This was not an inconvenient stop added to a direct journey. Jupiter was part of the mission's propulsion architecture. Its moving gravitational field could alter New Horizons' direction and increase its heliocentric energy without forcing the probe to carry the propellant required for an equivalent engine burn. New Horizons passed Jupiter along geometry chosen to produce an outward gain. The encounter bent the spacecraft's path and accelerated it relative to the Sun. It also aimed the probe more accurately toward the place where Pluto would be years later. The target was never Pluto's position on the day of launch. Mission planners had to intercept a moving world after both the spacecraft and Pluto had continued around the Sun. The Jupiter assist changed the duration of the mission dramatically. Without it, the journey on the available path could have taken about 14 years. With Jupiter's help, New Horizons reached Pluto in under 10, saving roughly 5 to 6 years depending on how the comparison is framed. This was not merely a matter of convenience. Mission duration affects spacecraft reliability, staffing, communication planning, and how long a power system must support the scientific encounter. After Jupiter, New Horizons entered the long, quiet portion of its journey. The engines did not fire continuously to drive the spacecraft across every remaining mile. Most of the time, it coasted along the trajectory established by its launch, Jupiter encounter, and occasional corrections. In space, motion does not require continuous thrust when there is little resistance. Engines are needed to change the path, not to keep an object moving along the path it already has. This coast can make the voyage sound effortless, but it was not inactive in the broader mission sense. The spacecraft had to preserve power and remain healthy across years of extreme distance. Its position and trajectory had to be measured from Earth. Corrections had to be planned carefully because even a small directional error could grow into a large miss by the time the probe crossed Pluto's orbit. The spacecraft also entered periods of hibernation to reduce wear and operational demands. New Horizons arrived at Pluto in July 2015 after about 9.5 years of travel. It had crossed more than 3 billion miles and reached the target with the timing needed to pass through a narrow encounter region. During that brief passage, its instruments collected the close observations for which the entire mission had been built. Then the spacecraft continued outward. It continued because the mission had never included the ability to stop. New Horizons passed Pluto at roughly 14 kilometers per second relative to the dwarf planet. Entering orbit would have required the spacecraft to remove a large share of that encounter velocity. Carrying the necessary braking propellant would have made the spacecraft heavier, which would have increased the demands placed on the launch vehicle and altered the fast trajectory that made the encounter possible. The mission also depended on accepting that speed creates limits. A faster cruise reduced the years needed to reach Pluto, but it compressed the encounter and increased the difficulty of stopping. The energy that made arrival possible made capture unrealistic. New Horizons could trade time against launch effort, but it could not gain a journey, a large payload, and an easy arrival together. Its design selected what existing technology could support. Reach Pluto, observe it closely, and keep moving. Pluto itself could not provide the same convenient braking architecture that Venus provided Parker across repeated encounters. New Horizons arrived once, at high speed, after a long outward journey. Without a sufficiently large propulsion system or another planned method of energy removal, the probe could observe Pluto only while flying past. This limitation was accepted from the beginning because a flyby could deliver valuable science within a realistic mass and energy budget. This is the trade at the heart of the mission. New Horizons reached an extraordinarily distant world by carrying a small payload, accepting a demanding high-energy launch, using Jupiter to gain speed and direction, and giving up the ability to remain at Pluto. Distance created a long delay and severe operating constraints, but it did not require the probe to cancel Earth's heliocentric motion before beginning the journey. Calling this route easier must therefore remain conditional. New Horizons required one of the most energetic launches of its time. Jupiter had to be encountered along the correct path. Pluto had to be met after almost a decade of flight. The spacecraft had one fast opportunity to collect its central observations. Navigation, power, communication, and reliability remained serious challenges throughout the voyage. Yet the mission architecture was achievable with chemical launch technology and a gravity assist. The outward route added energy to a motion the spacecraft already possessed. Jupiter then added more, shortening the coast. New Horizons did not fight its way across 3 billion miles through continuous thrust, and it did not attempt to erase its arrival velocity at Pluto. It followed a path whose greatest costs were concentrated in launch, timing, and the sacrifice of orbital capture. The result provides the outward counterpart to Parker's inward journey. Venus repeatedly reduced Parker's heliocentric energy so the probe could fall closer to the Sun. Jupiter increased New Horizons' heliocentric energy so the probe could reach Pluto sooner. Both planets changed spacecraft paths through gravity, yet the outcomes point in opposite directions. The difference cannot be explained by saying that Venus is a brake while Jupiter is an accelerator. Either planet can change a trajectory in more than one way if the encounter geometry allows it. The real answer depends on how a spacecraft approaches a moving planet, how gravity turns its path, and how that redirected motion appears from the Sun. The apparent conflict between Venus and Jupiter disappears when the encounter is viewed from the correct perspectives. A gravity assist is not a special power that belongs to one planet. It is an exchange between two moving objects inside a larger system. The spacecraft arrives with one velocity. The planet is already traveling around the Sun with another, and gravity changes the direction in which the spacecraft leaves. Whether the probe gains or loses heliocentric energy depends on how those motions fit together. Begin with a viewpoint moving alongside the planet. From this planet-relative frame, the spacecraft approaches from one direction, falls into the planet's gravitational influence, and follows a curved path. It becomes faster as it approaches because gravity pulls it inward. After passing the planet, it climbs away and gives back most of that temporary increase. In an ideal unpowered encounter, its departure speed relative to the planet is approximately equal to its approach speed, but the direction has changed. The planet has therefore acted like a device that turns the spacecraft's velocity. It has not simply added a fixed amount of speed. A shallow encounter may bend the path by a small angle. A deeper safe pass can bend it more strongly. The planet's mass, the spacecraft's approach speed, and the closest permitted distance all influence the turn. Real missions may use small engine corrections, but gravity supplies the central redirection. If we stop with this planet-relative view, the energy change around the Sun remains hidden. The incoming and outgoing speeds may look nearly equal, which makes acceleration or braking seem impossible. The missing piece is that the planet-relative frame is itself moving. Venus, Jupiter, and every other planet travel along their own heliocentric orbits while the encounter takes place. To see the mission result, the planet's orbital velocity must be combined with the spacecraft's motion relative to that planet. Before the flyby, these velocity directions form one arrangement. After gravity bends the spacecraft's path, they form another. Even if the spacecraft's speed relative to the planet remains almost unchanged, its total velocity relative to the Sun can be different. because the direction being added to the planet's motion has changed. A restrained comparison can make this clearer. Imagine a ball approaching a massive vehicle that is moving along a road. If the ball could be turned by the vehicle without a damaging collision, it might leave with more of its motion aligned with the vehicle's travel, or with less of it. The moving vehicle would influence the ball's speed as judged from the roadside. A planet performs a far smoother and more complex version through gravity rather than contact. The comparison should not be pushed too far. A gravity assist is not an ordinary bounce, and a planet's gravitational field acts across a curved three-dimensional trajectory. The useful point is that a moving object can redirect another object's motion and exchange energy with it. The outcome depends on the directions before and after the encounter, not on a permanent label such as accelerator or brake. When the departure geometry leaves more of the spacecraft's velocity aligned with the planet's orbital motion, the probe can gain heliocentric speed and energy. This is the familiar slingshot result. Mission descriptions sometimes say the spacecraft passes behind the planet and is pulled forward. That can be helpful shorthand, but the complete answer always depends on the three-dimensional path, timing, and reference frame. When the departure leaves less of the spacecraft's motion aligned with the planet's travel, the probe loses heliocentric speed and energy. Descriptions may say it passes ahead of the planet and is pulled backward. Again, this is an intuitive picture rather than a universal rule drawn on a flat page. Mission designers calculate the full encounter geometry rather than relying on the phrase alone. New Horizons met Jupiter in the arrangement that produced an outward gain. Jupiter's gravity turned the probe's path so that, after the encounter, its heliocentric motion carried more energy and pointed along the route needed for Pluto. The encounter shortened the journey because it changed both speed and direction in a useful way. Jupiter did not manufacture that energy from nothing. Parker met Venus through an arrangement chosen for the opposite outcome. The gravitational turn left Parker with less heliocentric orbital energy, allowing the next solar orbit to reach a lower perihelion. Repeated encounters accumulated the effect. Venus did not possess a special braking field. Parker approached and departed in geometry designed to produce braking when measured relative to the Sun. In both cases, the planet participated in the exchange. If a spacecraft gains momentum in one direction, the planet receives a corresponding change in the other. If a spacecraft loses heliocentric energy through an encounter, that energy is transferred within the system rather than destroyed. Conservation of momentum and energy remains satisfied. The planet's response is far too small to notice in its ordinary motion. Jupiter and Venus outweigh these spacecraft by an enormous amount. A change capable of transforming a probe's trajectory produces an immeasurably tiny alteration in a planet's orbit. The unequal masses allow the planet to behave like a vast moving reservoir while still obeying the same laws as the spacecraft. This also explains why the phrase free energy is misleading. A gravity assist can save onboard propellant, making the change effectively free from the spacecraft's fuel budget. But the energy comes from, or goes into the planet's orbital motion. The mission also pays in other ways: launch timing, trajectory constraints, additional travel, navigation precision, and dependence on the positions of moving worlds. Encounter timing is part of the physics rather than a scheduling detail. A spacecraft must reach the planet when the planet occupies the place in its orbit, and it must approach along the correct direction. Launching on another date can change the geometry or remove the opportunity entirely. This is why gravity-assisted missions are designed around launch windows and planetary positions instead of choosing the shortest line between two destinations. The encounter changes more than the number on a speedometer. By turning the velocity vector, a planet can aim the spacecraft toward a target that would otherwise require a powered maneuver. Jupiter helped New Horizons gain energy while redirecting it toward Pluto's position. Venus changed Parker's energy while setting up an orbit that could return for a later assist. Direction, energy, and timing were solved together. Treating the flyby as a boost or brake alone would miss its value. Venus could accelerate a spacecraft launched along a different path. Jupiter could remove energy from a probe arranged to leave the encounter differently. Planet size and location affect how useful an assist can be, but neither planet is locked into one role. Geometry controls the sign of the heliocentric change. The two missions can now be placed under one rule. Parker approached Venus so that gravity redirected its motion toward lower solar energy. New Horizons approached Jupiter so that gravity redirected its motion toward higher solar energy. In the planet relative frame, each spacecraft mainly turned. In the Sun relative frame, one slowed and the other accelerated. This resolves the second complication without changing the earlier answer. The close solar route remained difficult because Parker needed to remove energy, while the Pluto route could add energy and continue outward. Gravity assists made both missions practical by exchanging momentum with planets, but the required directions of those exchanges were opposite. Trajectory energy, however, is only one kind of difficulty. A successful path merely delivers the spacecraft into the region where its instruments must work. Close to the Sun, the probe faces intense heat and radiation. Near Pluto, it faces darkness, distance, weak power, and delayed communication. Once the motion problem is solved, the environments reveal two very different meanings of hard. A perfect trajectory can still deliver a spacecraft into an environment where it cannot survive or work. Reaching the correct region is only the first condition of success. The vehicle must remain powered, protect its instruments, follow commands, make decisions when Earth cannot respond quickly, collect observations during limited opportunities, and send the results home. Parker Solar Probe and New Horizons faced almost opposite forms of this problem. Parker moved into a region dominated by intense sunlight, heat, energetic particles, and radiation. As the spacecraft approached perihelion, the solar energy falling on each exposed area increased sharply. Electronics and scientific instruments could not simply endure the same conditions as the side facing the Sun. The mission needed a protected space behind a thermal shield, where sensitive systems could continue operating. The shield was not a decorative shell placed around the whole probe. It worked by standing between the Sun and the vulnerable spacecraft. Parker, therefore, had to maintain the correct orientation during its closest passes. If the shield faced the Sun as designed, much of the spacecraft remained in its shadow. If Parker turned too far away from that protective alignment, equipment not built for direct exposure could receive dangerous heat. Pointing was therefore part of survival, not merely a way to aim instruments. The spacecraft needed to know its orientation, control it, and respond safely when conditions changed. Earth could prepare plans and monitor the mission, but controllers could not guide every action in real time. Radio signals require time to cross interplanetary distances, and events aboard a fast-moving probe can develop before a human response returns. Parker needed onboard systems capable of protecting the spacecraft autonomously. Each low perihelion brought another period of concentrated operations. Parker did not face the Sun once and then leave the problem behind. Its orbit carried it inward repeatedly. The mission could learn from earlier passes, but the spacecraft also had to preserve its ability to survive and operate through later encounters. Intense exposure arrived in cycles, separated by wider parts of the orbit where conditions were less severe. New Horizons faced the other extreme. Far from the Sun, heat was not the central environmental threat in the same form. Sunlight became faint, the surroundings became cold, and the enormous distance from Earth shaped almost every part of the mission. A power system useful near Earth could not be assumed to work efficiently billions of miles away. Solar panels were not a practical primary power source for this New Horizons architecture at Pluto's distance. The spacecraft instead relied on a radioisotope power system, which produced electricity from heat released by radioactive material. This allowed the probe to operate where sunlight was weak, but the available electrical power remained limited. Instruments, communications, heaters, and onboard computers all had to live within that budget. Power management became more demanding as the mission continued. The spacecraft could not operate every system at full strength without consequence. Engineers had to decide which equipment should be active, when observations should occur, and how the vehicle could remain healthy during the long cruise. Hibernation reduced operating demands for extended periods, but the spacecraft still had to wake, check itself, receive instructions, and prepare for the encounter. Distance also weakened and delayed communication. A signal crossing billions of miles does not permit a live conversation between controllers and spacecraft. Commands sent from Earth take hours to arrive, and any reply requires another long crossing. By the time a problem becomes visible to the team, the event that caused it may already be far in the past from the spacecraft's viewpoint. The radio signal itself becomes extremely faint across that distance. Returning scientific information is not like transferring a file through a nearby network. Data must be transmitted carefully through a limited connection and collected by sensitive receivers on Earth. The observations gathered during the short Pluto encounter took far longer to return than they took to record. This changed how New Horizons had to operate at Pluto. The spacecraft could not wait for Earth to examine each image and choose the next action. It followed stored instructions, designed long before the closest pass. Those instructions controlled where instruments pointed, when measurements began, and how data were stored. The probe had to carry out the sequence while racing through the Pluto system. There was little opportunity for a second attempt. New Horizons did not settle into orbit and circle back after controllers reviewed the first results. Its high encounter speed created one brief passage. Years of travel and preparation led to a narrow period in which the spacecraft had to perform correctly. The value of the mission depended on reliable automation, careful planning, and accurate knowledge of the expected geometry. Parker also relied on autonomy, but its operational pattern was different. It returned to perihelion multiple times and faced repeated bursts of thermal and radiation intensity. New Horizons endured a much longer separation from Earth before a single rapid central encounter. One mission concentrated danger in recurring passes close to a star. The other concentrated uncertainty across distance, time, limited power, and a fleeting arrival. The missions experienced time in opposite ways. Near perihelion, Parker crossed its demanding region quickly because its speed became greatest there. Systems had to respond during a short interval of intense exposure. New Horizons also moved rapidly through its Pluto encounter, but that moment arrived after years in which equipment aged and available power declined. A short opportunity can therefore sit inside either repeated high-intensity cycles or a long period of isolation. Scientific return depended on designing around these limits. Parker's shield protected the spacecraft, but it restricted which directions could be exposed safely. New Horizons' power source enabled work far from sunlight, but it could not provide unlimited electricity. Autonomy reduced dependence on immediate commands, but stored instructions could not anticipate every condition. Each solution created boundaries that shaped what could be measured, when instruments could operate, and how much information could be preserved. The environment was not an obstacle added after the spacecraft was built. It influenced the design from the beginning. These differences resist a simple ranking. Parker's environment imposed extreme heat management and pointing requirements after an already difficult inward trajectory. New Horizons' environment imposed years of cold, weak sunlight, declining power, delayed communication, and isolated operation. Calling Pluto easier in every engineering sense would ignore most of what made its mission difficult. The title's claim remains strongest where it began: trajectory, energy, and propulsion. For a small flyby spacecraft, an outward Pluto path could be achieved through a powerful launch and Jupiter assist, while a close solar path demanded repeated removal of heliocentric energy. Beyond that comparison, the word easier must be divided into categories. The answer changes when the question shifts from getting there to surviving, communicating, measuring, or staying. This creates the next necessary test. Both spacecraft succeeded because they were allowed to keep moving. Parker swept through perihelion and climbed outward. New Horizons crossed the Pluto system and continued into the Kuiper belt. If reaching required either probe to stop, enter orbit, or land, the energy accounting would change again. The meaning of arrival now becomes the deciding issue. Both missions succeeded because neither spacecraft had to come to rest at its destination. New Horizons crossed the Pluto system and continued outward. Parker's solar probe swept through perihelion and continued along its orbit. The distinction may sound like a technical detail, but it controls a large part of the energy requirement. Passing a target, remaining near it, striking it, and landing upon it are different mission goals. New Horizons arrived at Pluto with a relative speed of roughly 14 kilometers per second. During the flyby, that speed allowed the spacecraft to cross the encounter region quickly and continue into the Kuiper belt. For orbital capture, however, the same motion would have become a burden. Pluto's gravity could bend the path, but it could not automatically remove enough energy to hold New Horizons in a closed orbit. The spacecraft would have needed to slow dramatically. Its engines would have had to produce a large braking change at arrival, or the mission would have needed another method of losing energy. New Horizons did not carry a propulsion system designed for that task. The fuel, tanks, engines, and structure needed for capture would have increased its mass long before the spacecraft reached Pluto. That added mass would have affected the entire mission. A heavier spacecraft would have demanded more from the launch vehicle. It might not have achieved the same fast Earth departure, or the same Jupiter-assisted path. If the mission preserved the larger payload, it might need a slower transfer that reached Pluto with a different encounter speed. That would extend the journey and change requirements for power, reliability, operations, and communication. There is no single modification called adding orbit. A Pluto orbiter must be designed around capture from the beginning. Its launch, cruise, navigation, propulsion, power, and scientific plan would all respond to the need to arrive slowly enough or brake strongly enough to remain. A Pluto lander would add another stage of difficulty, requiring a controlled descent and a way to function on the surface after arrival. New Horizons avoided those demands because its scientific goal could be served by a flyby. It exchanged time near Pluto for a lighter spacecraft and a faster journey. The probe gathered close observations during one passage rather than remaining to watch the dwarf planet change. That was a limitation, but it was also the decision that made the mission architecture achievable. The solar side of the comparison contains its own distinctions. Parker did not travel to a point above the Sun and stop. It remained in a highly stretched orbit around the Sun. At perihelion, it moved through the closest part of that orbit at enormous speed. Solar gravity then carried it onward, and the spacecraft later returned for another pass. A direct solar impact would be a different goal. An impact trajectory would need to reduce enough sideways motion for the spacecraft's path to intersect the Sun, but it would not need to cancel all speed at arrival. The spacecraft could strike the Sun while moving extremely fast, passing through part of the outer solar atmosphere, hitting the visible Sun, and establishing a tight repeating orbit are therefore separate trajectory problems. Hovering creates another misleading image. A spacecraft cannot park motionless above the Sun and remain there without support. Solar gravity would pull it inward. To hold a fixed position, the vehicle would need continuous thrust or another balancing force, creating an entirely different propulsion requirement. Parker never attempted this. Its speed and orbit were essential to its survival and continued motion. Landing is even less useful as a direct comparison. Pluto has a solid surface on which a suitably designed craft could attempt to land. The Sun does not. Its visible surface is a layer of glowing plasma rather than solid ground. A spacecraft entering deeper solar layers would encounter increasingly destructive conditions, not a landscape where engines could lower it onto stable terrain. These differences show why ordinary travel language can create false comparisons. On Earth, arriving, stopping, and staying often belong to the same action. In orbital flight, each requires a distinct change of velocity. A probe can reach the correct distance from a target while remaining on a path that immediately carries it away. Whether that counts as success depends on the mission's purpose. Arrival speed shows why distance and stopping cannot be separated. A spacecraft may spend years climbing outward and still reach its destination too quickly for capture. The journey does not automatically remove the energy added at departure. Likewise, a probe can approach the Sun and become faster as it falls inward, even after earlier maneuvers reduced its orbital energy. The stated encounter depends on the trajectory, not merely on how much space has been crossed. Mission designers can trade among these conditions, but every trade has a cost. A longer Pluto route may reduce braking needed at arrival, while demanding a spacecraft that remains useful for more years. A deeper solar orbit may improve access to the desired environment while requiring more energy removal and stronger protection. A flyby may fit within available mass while limiting observation time. An orbiter may provide repeated measurements while making launch and capture harder. These are not flaws added after the route is chosen. They are the route. Reached should describe the objective. New Horizons reached Pluto as designed, and Parker reached its solar region. Neither mission failed because it continued moving. The controlled comparison in this investigation is now precise. On the outer side is a New Horizons-class flyby, a small probe launched onto a high-energy outward path, accelerated and redirected by Jupiter, and allowed to continue after crossing Pluto. On the inner side is a Parker-class solar pass, a protected probe placed in heliocentric orbit, repeatedly slowed through Venus encounters, and allowed to sweep through a very low perihelion before climbing outward again. Under these definitions, the title remains defensible. The Pluto flyby could be achieved by adding outward energy through a powerful chemical launch and a gravity assist. The close solar pass required a far greater reduction of the heliocentric motion inherited from Earth, forcing Parker to use repeated planetary braking over several years. The distant target fit more naturally into an outward escape-style architecture than the nearby Sun fit into a deep inward one. That conclusion does not mean every Pluto mission is easier than every solar mission. A fast solar impact might be compared with a Pluto orbiter and produce a different practical ranking. A Pluto landing, a permanent orbital platform, or a sample return mission would introduce requirements that New Horizons never faced. Likewise, changing the desired solar distance would change the inward energy burden and thermal conditions. Qualification does not weaken the paradox. It reveals exactly where the paradox lives. The surprising result is not a vague statement that Pluto is easy or that the Sun is impossible. It is a specific fact about motion from Earth. A small spacecraft can be placed on an outward path that intersects Pluto more readily than it can be placed on an orbit passing extremely close to the Sun. The verbs now match the physics. Fly past Pluto. Pass close to the Sun. Do not silently replace one with orbit, landing, or hovering. With those endpoints fixed, the two journeys can finally be returned to the same starting point and compared in one complete account. The remaining question is no longer what reaching means, but why the energy balance favors the path toward Pluto. The comparison can now begin from a single shared moment. Place New Horizons and Parker Solar Probe near Earth before their paths separate. Both spacecraft belong to a planet moving around the Sun at a mean speed of about 29.78 kilometers per second. Both inherit that motion. Neither waits motionless in space for a rocket to choose a destination. The central difference lies in what each mission must do with the velocity it already possesses. Most of that inherited motion runs tangentially across the sunward direction. It is the motion that keeps Earth circling rather than falling directly into the star. From this starting state, Pluto and the Sun are not simply points at different distances. They represent changes in opposite directions through orbital energy and angular momentum. For the Pluto flyby, mission planners needed to raise the spacecraft away from Earth's solar orbit. New Horizons received an exceptionally energetic launch. It departed Earth at roughly 16.2 kilometers per second relative to our planet, with a C3 near 158 square kilometers per square second. These figures describe the power of its departure, not its speed at every later point. The launch was aimed so that its contribution worked with Earth's heliocentric motion and placed New Horizons on a high-energy outward path. The spacecraft did not have to erase the solar velocity it inherited and then begin again. It used that moving foundation, added the required departure change, and entered an orbit stretching into the outer solar system. Jupiter then extended the same outward strategy. Its gravity redirected New Horizons and increased the probe's energy relative to the Sun. The encounter shortened the journey and aimed the spacecraft toward Pluto's future position. After that, the probe could coast for most of the remaining distance. Its engines corrected the route, but they did not push continuously across billions of miles. At Pluto, the architecture preserved its central advantage by allowing the spacecraft to remain fast. New Horizons arrived at approximately 14 kilometers per second relative to the dwarf planet, collected observations during the flyby, and continued outward. It did not pay the enormous additional cost of canceling that arrival speed for orbital capture. Its mission counted intersection as success. Parker's requirement pointed the other way. To pass extremely close to the Sun, the spacecraft had to lower the solar orbit it inherited from Earth. Solar gravity was already pulling on it, but gravity alone did not remove the tangential motion and angular momentum that kept the probe circling. Parker needed to shed heliocentric orbital energy before the Sun could draw it into a sufficiently deep path. A direct chemical attempt to remove most of that motion would demand a velocity change in roughly the 24 to 30 km per second class. The range depends on assumptions: where the maneuver begins, which solar endpoint is chosen, how Earth escape is counted, and whether planetary assistance is allowed. It is a model-based mission estimate, not one exact value belonging to every solar trajectory. Even the lower end creates a severe practical burden. Chemical propellant must be accelerated before it can be expelled, so the mass requirement compounds as delta V rises. Tanks, engines, and stages add more mass. A mathematically valid direct path can therefore leave almost no useful capacity for the shield, instruments, communication equipment, power system, and guidance hardware that turn a trajectory into a scientific mission. Parker solved this not by overpowering the energy requirement, but by changing how the energy was removed. A powerful launch established its first useful solar orbit. 7 encounters with Venus then reduced its heliocentric energy step by step. Each gravitational turn lowered a later perihelion without forcing Parker to carry the propellant for an equivalent sequence of engine burns. Once Parker had lost enough orbital energy, it could fall deeply toward the Sun. Gravity accelerated the spacecraft during that fall until it reached roughly 430,000 miles per hour near perihelion. This record speed is sometimes presented beside launch speeds as if the larger number proves a more powerful rocket. It does not. Parker became so fast near the Sun because its earlier trajectory allowed gravity to convert a deep fall into motion. This creates the central contrast. New Horizons needed added heliocentric energy, so its orbit could stretch outward. Parker needed removed heliocentric energy, so its perihelion could fall inward. Adding enough energy for a small Pluto flyby payload was difficult, but achievable through a powerful chemical launch and Jupiter assist. Removing enough energy for a Parker-class solar pass demanded a powerful launch plus 7 Venus assists spread across years. The billions of miles to Pluto dominate a map, but the map does not show the spacecraft's initial velocity. The Sun is close in position, yet difficult in velocity space. Pluto is remote in position, but an outward flyby can follow a path that builds on the direction Earth already travels. The mission does not need to cross every mile by burning fuel. It needs the correct initial state and gravitational encounters, after which motion continues naturally. The difference can be expressed without treating either trajectory as a straight road. Draw one arrow for Earth's motion around the Sun. The Pluto mission begins by extending and redirecting that arrow into an outward path. The solar mission begins by shortening its sideways part so gravity can bend the path inward. The spacecraft are not paying for opposite distances. They are paying for opposite changes to the inherited velocity. This is why aiming at the Sun cannot solve the problem. Orientation tells the spacecraft which way its instruments or engines face, but velocity determines where its mass continues moving. A brief engine burn can reshape an orbit, yet the vehicle must supply enough change in the correct direction. When tangential motion is large, a line of sight to the Sun offers no shortcut around energy removal. Actual mission outcomes provide the strongest reality check. A compact spacecraft left Earth on a high C3 path, used Jupiter, and crossed Pluto's position within a decade. A protected probe entered the solar corona, but only after a powerful launch and a staged sequence of 7 Venus assists. These are not abstract competing calculations. They are 2 completed demonstrations of how difficult trajectories are built from Earth. The contrast remains causal rather than rhetorical. Parker did not need repeated Venus encounters because the Sun was physically far away. It needed them because Earth supplied the wrong kind of motion for a deep inward pass. New Horizons did not reach Pluto because distance became irrelevant. It reached Pluto because its architecture accepted the costs of distance while avoiding the greater cost of stopping at arrival. Several measurements can obscure this result if they are mixed. Distance tells how much space separates locations. Travel time tells how long a selected trajectory lasts. Delta V describes the propulsive change a vehicle must provide. C3 characterizes excess Earth departure energy. Encounter speed compares a probe with its target, while heliocentric speed compares it with the Sun. Peak speed may be produced largely by gravity rather than engines. None of these measurements can replace all the others. New Horizons' 16.2 km per second Earth departure cannot be placed directly beside Parker's 430,000 mile per hour perihelion speed to decide which launch was harder. Parker's peak came in a deep gravitational field after years of orbital shaping. New Horizons figure described departure from Earth. They answer different questions. NASA's statement that reaching the Sun requires about 55 times more energy than reaching Mars reinforces the same counterintuitive lesson. It shows why a nearby sun can demand more than a more distant planetary route. But it remains a Mars comparison given in Parker's mission context. It cannot honestly be converted into a claim that the Sun is exactly 55 times harder than Pluto. There is no single universal Sun versus Pluto multiplier. To calculate one, we would need to fix the payload, launch vehicle, starting orbit, propulsion system, departure date, planetary assists, travel time, solar perihelion, and definition of arrival. Change any of these, and the result changes. A clean documentary answer should preserve the strong qualitative comparison without manufacturing false precision. The evidence falls into different levels of certainty. Earth's orbital motion, the launches, the planetary encounters, and the achieved flybys are observed mission facts. The way gravity assists exchange energy is established orbital mechanics. Estimates for a direct solar trajectory are model-dependent because they rely on chosen assumptions. The word easier remains definition-dependent because an orbiter, lander, impactor, and flyby do not share the same objective. Within the definitions fixed here, the answer is direct. Reaching Pluto is easier than flying close over the Sun because an Earth-launched spacecraft already carries enormous sideways motion around the Sun. A Pluto flyby can use that motion, add outward energy, gain more from Jupiter, and remain fast when it arrives. A close solar pass must shed much of that inherited motion before gravity can pull the spacecraft into a deep enough orbit. Pluto is farther away in kilometers. The Sun is farther away in the change of motion required from Earth's starting state. That is the paradox resolved. The answer does not make New Horizons simple. Its launch was demanding, its journey lasted almost a decade, and its fast encounter sacrificed the ability to stay. Nor does it make Parker's path impossible. Venus made the required reduction achievable by replacing an overwhelming direct propellant burden with repeated gravitational exchanges and precise navigation. The comparison instead reveals the deeper rule governing both missions. Space travel is not movement across a stationary map. It is movement from one existing orbit into another trajectory. Every departure begins with velocity, and every destination must be reached by transforming that starting state. Distance matters for time, communication, power, and reliability, but it does not alone set the propulsion price. This completes the scientific argument. The Pluto flyby wins the defined energy comparison because it adds to and redirects inherited motion, while the Parker-class solar pass must first remove a much larger share of that motion. The result belongs to the mission architectures humans can currently build with chemical propulsion and planetary assistance. That final condition leaves one legitimate question open. The laws of motion will not change, but the machinery used to exchange momentum might. If a spacecraft could accelerate efficiently for months or receive momentum without carrying all its reaction mass, the practical cost of both journeys could shift. Future propulsion may change which route engineers call easier, even though it cannot erase the orbital physics that created the paradox. The answer can change in engineering terms without changing in physical terms. Future spacecraft will still leave Earth with inherited heliocentric motion. They will still need to add energy for some trajectories, remove it for others, and manage angular momentum when moving closer to the Sun. Conservation of energy and momentum will continue to govern every route. What technology can change is the cost, speed, and practical method of producing the required transformation. Chemical rockets perform this task by carrying propellant and expelling it at high speed. Their greatest advantage is strong thrust. A chemical stage can produce a large change during a short burn, which is essential for launching from Earth and useful when a maneuver must occur at a particular point. Its limitation is the mass relationship already seen. The vehicle must carry the material it will later throw away, and extreme delta V rapidly consumes the payload budget. Electric propulsion offers a different trade. Instead of burning chemical propellant in a brief, powerful reaction, an electric system uses electrical energy to accelerate a smaller amount of propellant to much higher exhaust speed. This can provide far more change in velocity from a given propellant mass. The underlying principle has already been demonstrated in space, although individual systems differ greatly in power and mission role. The gain in efficiency normally comes with low thrust. An electric engine may push gently for weeks, months, or longer rather than delivering one enormous impulse. That continuous effort can gradually reshape a spacecraft's orbit. It could reduce the propellant mass required for some inward or outward journeys, but the longer thrust period changes mission time, power needs, navigation, and spacecraft design. Electric propulsion does not make the orbital energy requirement vanish. The spacecraft still has to exchange momentum with expelled propellant. It must still reduce tangential motion for a deep solar approach or add the appropriate energy for an outward route. The technology changes how efficiently that work is performed, not the amount of orbital transformation the destination requires. Power availability also matters. An electric engine needs a source of electricity, and the useful power system may change as the spacecraft moves through the solar system. A design intended to thrust close to the Sun faces different conditions from one expected to operate far beyond Earth. Greater efficiency in propellant can therefore create new demands in electrical generation, thermal control, and operating time. Solar sails move the exchange outside a conventional rocket engine. Light carries momentum. When sunlight strikes and reflects from a large, lightweight sail, it produces a small force. The spacecraft can use that force without consuming chemical propellant for every change in velocity. The physical principle has been demonstrated, making solar sailing more than an imaginary effect. The available force is gentle and depends on the light reaching the sail. Sail area, total mass, reflectivity, orientation, and material strength all shape the result. A sail cannot choose any acceleration in any direction at any moment. It must tilt relative to the incoming sunlight, trading the size of the force against the direction in which that force acts. This can create new strategies for changing solar orbits. A sail may add or remove orbital energy gradually by maintaining the proper orientation over time. Because sunlight becomes stronger closer to the sun, some concepts can use a close solar passage to obtain a larger effect. Yet reaching that useful geometry still requires careful management of the initial orbit, and the sail must survive the conditions it encounters. Solar sailing, therefore, changes the propellant problem without abolishing trajectory design. The spacecraft receives momentum from sunlight rather than carrying all the reaction mass on board. It remains bound by available force, direction, time, and material limits. A sail could make some mission architectures more attractive, but it does not turn the solar system into a place where a vehicle can move freely between any 2 points. Beamed sails extend the external source idea. Instead of relying only on natural sunlight, an outside system would direct energy toward a sail and transfer momentum to it. The spacecraft would not need to carry the full energy source used for acceleration. In principle, this could produce new combinations of payload and speed. For the journeys considered here, however, large beamed systems remain developmental or speculative mission applications. The physical exchange of momentum is sound, but practical questions of beam power, pointing, infrastructure, sail materials, distance, and control are substantial. It would be misleading to assign a promised travel time or claim that such a system will certainly reverse the Sun-Pluto comparison. Nuclear and other advanced propulsion concepts could also alter the trade between thrust, efficiency, payload, and mission duration. Some underlying technologies are established in limited roles, while particular high-performance mission designs remain under development or beyond demonstrated capability. Without a fixed vehicle and trajectory, their effect cannot be reduced to one reliable number. The distinction between levels of maturity is essential. A demonstrated physical principle shows that an effect is real. A developing engineering capability shows that hardware can be improved toward useful missions. A speculative application asks what might become possible if several unresolved systems work together. Moving from the first level to the third does not provide evidence that a proposed mission can already be flown. Future propulsion may make one route faster, allow a larger payload, reduce launch mass, or avoid some planetary assists. A long-duration electric system might gradually perform changes that are too costly for chemical stages. A sail might exchange momentum with sunlight. An external beam might move much of the energy source away from the spacecraft. Each possibility changes the engineering balance differently. A design might combine methods instead of selecting one. Chemical stages could provide departure thrust, electric propulsion could reshape the crew's trajectory, and a planetary encounter or sail could supply another change without a large chemical burn. Such combinations would not make the comparison obsolete. They would show that mission difficulty can be redistributed among launch mass, travel time, power, navigation, infrastructure, and risk. This is the boundary between confidence and possibility. We can state that efficient momentum exchange changes mission design because that follows from established physics. We can discuss demonstrated electric engines and solar sailing as real technologies. We can explore beamed or nuclear applications as possibilities. We cannot claim that an undefined future vehicle has made the close Sun easier than Pluto. Without fixed assumptions, that conclusion would repeat the mistake of judging both journeys by distance alone. None removes the need to define the mission. A Pluto flyby, Pluto orbiter, solar impact, and low perihelion probe will still require different arrival states. A propulsion system that improves one may not improve another by the same amount. Mission duration, power, heat, communication, and payload will continue to compete. The current answer, therefore, remains intact within its stated boundary. With chemical propulsion and planetary gravity assists, a New Horizons-class Pluto flyby can build on Earth's motion, while a Parker-class solar pass demands repeated removal of heliocentric energy. Future machinery may change the cost of that work. It cannot change why the work points in opposite directions. The uncertainty ends there. Predicting which technology will dominate would replace evidence with confidence we do not possess. What remains certain is the starting condition beneath every design. A moving Earth gives each spacecraft a motion before its engines begin. The final meaning of the paradox lies not in a future engine, but in recognizing the moving world from which every journey starts. Every mission begins on a world that is already going somewhere. Long before a countdown reaches zero, before engines awaken or a spacecraft rises from its launch pad, Earth is carrying the entire vehicle around the Sun. The probe does not leave a motionless home and enter a moving universe. It begins inside the motion of its home and carries part of that motion into everything that follows. From the ground, this is easy to forget. The landscape appears stable. The Sun crosses the sky with such regularity that it can seem like the moving object, while Earth feels fixed beneath our feet. Our maps encourage the same picture. They place planets at different distances and invite us to imagine journeys as lines drawn between them. The shorter line appears easier because in ordinary life, it usually is. But a map of positions cannot show the complete starting condition. Earth is a moving platform, and every destination is moving too. A route through the solar system is not simply a line across empty space. It is a change from one motion into another. The spacecraft must inherit, add, remove, redirect, or exchange velocity before the desired path can exist. This does not make distance meaningless. Pluto's distance created years of travel, faint signals, limited power, and a brief encounter reached after an enormous crossing. The Sun's closeness brought heat, radiation, and demands that no distant cold world could reproduce. Distance shaped both missions. It simply did not decide the central energy comparison by itself. New Horizons succeeded because its route used the movement already available. Its launch added to an inherited heliocentric path. Jupiter redirected that motion and contributed more energy to the outward journey. The spacecraft crossed Pluto's position while still moving quickly, accepted that it could not stay, and continued into the darkness beyond. Parker's solar probe succeeded by doing something less intuitive. It surrendered orbital energy. It returned to Venus repeatedly, allowing the planet's motion and gravity to reshape the probe's path a little more each time. Only after giving up enough of the sideways motion inherited from Earth could Parker fall into the region where the Sun accelerated it to record speed. These achievements appear opposite, but they express the same kind of intelligence. Neither mission defeated gravity. Neither forced the solar system to behave like a stationary map. Engineers learned what motion was already present, calculated how planets could exchange energy with a spacecraft, and designed each journey around those relationships. Human exploration often looks most powerful when a rocket leaves the ground in fire. Yet the deeper achievement can be quieter. It lies in recognizing that a planet encountered years later can perform part of a maneuver. It lies in accepting a long coast instead of pushing continuously. It lies in knowing when gaining speed solves a problem, and when losing energy opens the only useful path. Working with nature does not mean the journeys were effortless. The launch vehicles still had to perform near their limits. Spacecraft had to survive environments at opposite extremes. Navigation teams had to predict meetings among moving objects across years and billions of miles. Instruments had to collect their observations during passages that could not simply be repeated on demand. The laws that restricted each mission also made its solution possible. Earth's motion created the barrier to a direct solar fall, but that same motion gave outward missions a moving foundation. Venus and Jupiter could redirect the probes because planets carry immense momentum along their orbits. Solar gravity prevented Parker from hovering, yet it also accelerated the spacecraft after its orbit had been lowered. Constraint and opportunity were never separate. They were different faces of the same physical system. The motion that closed one route opened another. The gravity that made a direct plan impractical made an indirect plan possible. Exploration advanced not by escaping these relationships, but by understanding them with enough accuracy to use them. This changes how our place in the solar system can be imagined. Earth is not merely the point marked home at the center of a diagram. It is a vehicle on a continuous path, carrying oceans, cities, launch pads, and every unfinished spacecraft through space. We live inside an orbit so steady that its enormous speed feels like rest. The same is true of our apparent stillness at any moment. A person looking at the sun from a quiet field is moving with Earth. Seen from the sun, the observer, the field, and the entire world sweep sideways together. Every spacecraft takes part of that hidden journey with it. Rockets do not create all motion from nothing. They modify a motion already given by Earth's rotation, orbit, and gravitational surroundings. The destination becomes reachable when that inherited state is transformed into the path the mission needs. That recognition offers a restrained form of humility. The solar system does not arrange itself around human ideas of near and far. It does not treat a visible destination as easy or a distant one as impossible. Our intuition was built for walking across landscapes that seem still, not for changing orbits among worlds moving at many kilometers per second. The success of Parker and New Horizons shows that intuition can be corrected. Measurements replace appearances. Motion replaces the static map. A paradox that first seems absurd becomes a clear result of the starting conditions. We do not lose wonder when the mechanism is understood. The wonder becomes more precise. Return, then, to the spacecraft imagined above Earth at the beginning. The sun fills the view ahead. Pluto remains an unseen point across the outer darkness. Nothing about their physical distances has changed. The sun is still near, and Pluto is still billions of kilometers away. What has changed is the meaning of the spacecraft's position. It is not suspended at rest above a stationary planet. Earth is carrying it sideways around the sun, and that inherited motion remains even after the spacecraft leaves. Pointing toward the light does not remove what the vehicle already carries. Gravity pulls inward, but the spacecraft continues across the fall. The direct route disappeared because it was never truly there. In its place is a richer picture. 2 moving probes, 2 moving planets, 1 moving Earth, and journeys created by exchanging energy within the system. Pluto can be reached by building on the motion of home. The Sun can be approached only after much of that motion is surrendered. The hardest part of reaching the Sun is letting go of the motion Earth has already so silently given us.